Have you ever looked at a really complex system? Maybe a huge website or like a global shipping network, even the human body, and just wondered how it manages itself.
Yeah,
Like it's got this hidden brain making decisions, scaling up or down, recovering from problems, all without someone constantly tweaking it.
it definitely feels like magic sometimes, doesn't it?
Yeah.
But yeah, it's not quite magic.
Right. But it has that same feeling of wonder, I think, when you see a really well-designed system just work.
Exactly. And that idea, that intelligent self-management, that's pretty much what we're going to dig into today.
Perfect. Yeah, we're zooming right in on the brain of Kubernetes, that open source platform that's basically changed the game for deploying and managing containerized apps.
Right.
So our mission today really is to give you a shortcut to understanding how this incredibly powerful kind of distributed system actually thinks, how it operates. So you'll walk away with a much clearer picture, hopefully, of how all the pieces fit together to, orchestrate your applications almost like it's doing it on its own.
Yeah, we're diving deep into the control plane.
Mm-hmm.
You can sort of think of that as the central nervous system for Kubernetes.
Okay.
We'll unpack the four main parts: the API server, etc., the scheduler, and the controller manager.
Got it.
But before we jump right into those, maybe we should quickly cover a few basic terms. Just make sure we're all grounded.
Good call. Yeah, good idea. So, okay, when we talk Kubernetes, you hear certain words all the time. First, cluster.
Right.
That's basically just a set of machines, nodes, all connected and working together to run your apps.
And those nodes, they're the worker machines, right? Doing the actual work.
Exactly, the heavy lifting.
And running on those nodes are the pods.
Ah, pods, yeah.
These are like the smallest things you can actually deploy in Kubernetes.
Right.
The basic building blocks. A pod usually holds one container, sometimes more, but it wraps up your application code and, everything it needs to run. Dependencies, libraries, all that.
Gotcha. Self-contained packages. And how do we, talk to this whole thing? How do we give it instructions?
That's where kube-ectl comes in, Kubectl.
Right, kube-ectl.
It's the command line tool, your main way to interact with the cluster, sending commands to the Kubernetes system.
Okay. So all these big decisions, though, like where to run those pods, how to scale things up or down, that's happening somewhere else, right? In the control plane.
Precisely. The control plane. That is the brain of the Kubernetes cluster. Often it runs on its own dedicated machines, the master nodes, and it's responsible for all those high-level decisions. Where workloads run, how to react to changes in demand, and really importantly, how to recover if things go wrong. It's like the conductor of the orchestra.
Okay, the conductor. I like that. So
Okay.
let's start dissecting this brain. Where does the input come from? The API server feels like the logical place to start, right?
Absolutely.
Yeah.
The API server, technically kube-apiserver, is absolutely central. It's the main interface for, well, everything happening in the cluster.
The front door.
Exactly. The front door, the universal translator, maybe even the bouncer. It exposes the Kubernetes API, handles all those RESTful API requests.
So requests coming from me using kube-ectl or from other parts of Kubernetes itself.
Both, yeah. Anything interacting with the cluster state goes through the API server.
So when I type like kube-ectl create deployment my app that hits the API server first, what happens then? Does it just pass it along?
Oh, no, it's much smarter than that. First, it validates the request. Is it formatted correctly? Does it make sense in Kubernetes terms?
Right.
Then, crucial step, authentication and authorization.
Yeah.
Who are you, and are you actually allowed to create a deployment?
Right, security first.
Always. Only after it passes those checks does it actually process the command and start coordinating the necessary actions with other parts of the control plane.
That sounds pretty robust. And you said it handles communication from other components too, so it's not just for users.
Not at all. It's the central hub for all communication within the cluster. Nodes talk to it, controllers talk to it, everything funnels through the API server.
Okay.
But one of the really powerful things about it, beyond just being a gatekeeper, is its extensibility.
Extensibility, how so?
Through something called custom resource definitions, or CRDs, you can basically teach Kubernetes about new kinds of resources, things specific to your applications.
Wait, so if I have like a special type of database or, I don't know, a custom machine learning model set up?
Exactly. You can define that it's a custom resource, give it its own API within Kubernetes, and then the API server lets you manage it just like you'd manage a standard pod or deployment.
Wow, so Kubernetes can actually learn my application's specific components.
Pretty much. It makes the system incredibly adaptable to whatever you need to run. It's not forcing you into just its own predefined boxes.
That is really powerful. Okay, so the API server is handling all these requests, validating them, passing them on. But where does all that information go? Where does Kubernetes store the state of everything? How does it remember what's supposed to be running?
Ah, right. That leads us directly to etc. etcd.
Etc. Okay.
Think of etc. as the cluster's memory, its database. It's a distributed, consistent key value store.
Key value store, like a dictionary.
Sort of, yeah. But highly reliable and distributed, it holds all the configuration data and the current state of every single object in your cluster. Every pod, service, deployment, what you want it to be, and what it actually is right now. It's the single source of truth.
So if I tell Kubernetes I want, say, 3 replicas of my web server, that desired number 3 gets stored in, etc.
Precisely.
And if one of those pods crashes, the actual count drops to 2.
Yeah.
That change is also reflected in, etc.
Exactly. Both the desired state, what you asked for, and the actual state, what's currently running, are tracked there.
And you said distributed and consistent. Why is that so important?
Well, imagine a huge cluster, hundreds of nodes. If different parts of the system had different ideas about the current state, it'd be chaos.
Wow.
Total chaos.
Yeah.
Etc. Uses clever algorithms like Raft to guarantee strong consistency. Every part of the system, every component reading from etc. sees the exact same up-to-date information, always. That consistency is absolutely fundamental.
Okay, that makes sense. How does it keep everyone updated so quickly when things change? Does everyone just constantly ask, etc., what's new?
Not quite constantly polling. It has a really neat watch functionality. Components can basically subscribe to changes for specific data they care about.
Subscribe, like notifications.
Yeah, exactly. So when something changes in, etc., to say the new pod's configuration is written, any component watching, that type of data gets notified immediately.
Ah, so it's event-driven. That's efficient.
Very efficient. It allows the whole system to react in near real time without components constantly hammering the database.
So the API server and etc. work hand in glove then. The API server is the gatekeeper for reading and writing to etc.
Exactly. The API server is essentially the only component that should talk directly to etc. It validates requests, then writes the changes to etc. When other components need information, they ask the API server, which reads it from etc.
Okay, so updating an app. I tell the API server, it validates, writes the desired change to, etc.
And then other components, watching etc. via the API server, see that change and start taking action to make it happen. It's this continuous feedback loop.
Right. So we've got the command center, the API server, and the clusters, memory, etc. Now, once we've told Kubernetes what we want, like, I need a new pod with these specs, who actually figures out where to put it, on which node?
Ah, that's the job for the matchmaker. That's the scheduler, or kube-scheduler.
Scheduler, okay.
Its whole purpose in life is to take newly created pods that exist in etc., but don't yet have a node assigned, and decide which node is the best fit for them.
Best fit. So it's not just finding any node with space.
Nope. It's smarter than that. It looks at the pod's requirements, CPU, memory, maybe special hardware like GPUs. Then it filters the available nodes to find ones that can satisfy those requirements.
Okay, filtering makes sense.
And then, from the nodes that can run the pod, it scores them based on various factors to find the best one. Maybe spreading pods out evenly, or maybe preferring nodes that already have the container image cached.
So it's doing optimization, too.
Exactly. Resource optimization is key. But it also considers policies you define. Like, you might use node affinity rules.
Affinity, like preferring certain nodes.
Yeah, you could say, I prefer this pod runs on a node with an SSD, or this pod must run in availability zone US East 1. The scheduler respects those rules.
What about keeping pods off certain nodes?
Yep, that's done with taints and tolerations. You can taint a node. Maybe it's reserved for special workloads or undergoing maintenance.
Like putting up a keep out sign.
Kind of. By default, pods won't be scheduled onto tainted nodes unless they have a matching toleration. It's a way to reserve nodes or repel certain workloads.
So you could use that to keep, say, general web servers off your expensive GPU nodes.
Precisely. Or ensure only your monitoring agents run on the master nodes. Gives you really fine-grained control over placement.
Okay. So the scheduler finds the right home for new pods based on needs, available resources, and all these rules.
Right. It ensures efficient use of resources, helps with fault tolerance because it won't place pods on unhealthy nodes, and it's even pluggable if you have really complex custom scheduling needs.
Okay, command center, API server, memory, etc., placement agent, scheduler. But systems aren't static, are they? Nodes fail, demand spikes, we need to update our apps. Who's the one constantly watching and making sure reality matches our desired state?
Now we get to the real enforcer. That's the controller manager or kube controller manager.
Controller manager. Okay, sounds important.
It is. It's kind of the engine that drives the cluster towards the state you defined in, etc.
Mm-hmm.
It's not actually a single thing, though. It runs multiple independent controller processes inside it.
Multiple controllers, like specialists.
Exactly. Each controller is like a little automated loop watching a specific part of the cluster. It looks at the desired state from, etc., via the API server, compares it to the actual current state, also observed via the API server, and if they don't match, it takes action to fix it.
So back to my example. Desired state says 3 replicas, but the controller sees only 2 running.
The relevant controller, probably the deployment or replica set controller, will notice the discrepancy and tell the API server, hey, we need to create another pod for this deployment.
And then the scheduler picks that new pod up and places it.
You got it. See how they work together.
Yeah.
The controller manager identifies the need, creates the pod object via the API server, etc., stores it, and then the scheduler finds it a home.
It's a constant reconciliation loop.
Constant reconciliation. That's the core idea. These controllers manage things like scaling applications, handling rolling updates smoothly so you don't have downtime,
Rolling updates, yeah, that's huge.
and recovering from failures. If a node goes down, a controller notices the pods on that node are gone and works to get them replaced on healthy nodes.
Can you give examples of a few key controllers inside the manager?
Sure. There's the replication controller, or the newer replica set controller. Its job is simple. Make sure the right number of pod replicas exist.
Okay, the counter.
Then there's the deployment controller, which manages higher-level application deployments, orchestrating those rolling updates, and enabling easy rollbacks if something goes wrong.
Update manager.
The node controller is crucial. It watches the health of all the nodes in the cluster. If a node becomes unreachable, this controller marks it as unhealthy and eventually evicts the pods that were running on it so they can be rescheduled elsewhere.
Ah, the health monitor for machines.
Right. And maybe one more, the service controller. When you expose your application using a Kubernetes service, this controller makes sure the underlying networking rules or cloud load balancers are configured correctly to send traffic to the right pods.
The network plumber.
You can say that. There are many others, but those give you a good sense of the different specialized tasks being handled automatically.
So the scheduler places new pods, but the controller manager is the one making sure the right number of pods exist, that deployments roll out correctly, that failed nodes are handled, always driving towards that desired state, and etc.
Exactly. And notice both the scheduler and all those controllers inside the controller manager, they all rely on the API server to get information from, etc., and to make changes to, etc. The API server is still that central gateway.
It really ties everything together.
It does. It's a continuous self-healing loop. Scheduler reads from, etc., via API server to place. Controller manager reads from, etc., via API server to check state, and writes back to, etc., via API server to make corrections.
It's becoming much clearer now how these 4 pieces, API server, etc., scheduler, controller manager, really form this, this coordinated brain for Kubernetes.
Yeah, the API server is the communication hub and gatekeeper. Etc. is the reliable memory, the source of truth. The scheduler is the smart resource matchmaker. And the controller manager is the tireless enforcer, always reconciling actual state with desired state.
Understanding this interaction really shows how Kubernetes pulls off that automation for complex stuff like scaling and self-healing. It's not just magic, it's these components working together.
Absolutely.
Yeah.
And grasping this isn't just, academic. It's key to understanding how to build and manage applications that are truly scalable and resilient using Kubernetes. It demystifies how it achieves that power.
Definitely a crucial step if you really want to master Kubernetes.
Yeah, sure.
Okay, so this leads to maybe a final thought for everyone listening. We've kind of unpacked this intricate self-regulating brain, right? This Kubernetes control plane, constantly comparing what we want with what we have. What is this model, this whole desired state versus actual state reconciliation? Tell us about managing complex systems, maybe even beyond just software.
That's a fascinating question. I mean, think about it. Could you apply this pattern, desired state, a central record, a placement or allocation function, and these diligent controllers elsewhere?
Like in business, a company strategy is the desired state, maybe market data is the etc., resource allocation is scheduling, and managers or teams are the controllers trying to align operations with the strategy.
Potentially, yeah. Or even think biologically.
Yeah.
DNA holds the desired state blueprint, right?
Yep.
And complex cellular machinery acts like controllers, constantly building, repairing, responding to keep the organism functioning according to that blueprint.
Huh. So what other hidden brains, these orchestration systems, are quietly running things all around us? And maybe more importantly, how can understanding their core parts, the communication hub, the memory, the allocator, the reconcilers, help you navigate or even build the complex systems of the future?
Something to definitely think about. How does this pattern repeat itself? Where else could we apply it?
Yeah, definitely food for thought.